Building Construction for the Fire Service, Week 6, Homework Problem 3. So this is a truss that you need to find some forces in, and the first piece, the simplest piece, I guess, is to find the reactions. So if I think about kind of my fundamental formulas for static equilibrium, I have the sum of all of the forces in the x direction must equal 0, and the sum of all of the forces in the y direction must equal 0, and the sum of all of the moments must equal 0. So I look at this diagram and I don't see any left or right forces. There are no vectors pointing left or right, so I don't need to do anything with the forces in the x direction. In the y direction, it's going to be the sum of all of these forces plus the reactions provided by the rollers at point A and the pin joint at point G. So if I think about the sum of the forces in the y direction, it's negative 10,000, and it's negative, remember, because it's a downward force, plus 15,000, I'm sorry, negative 15,000, plus negative 20,000, plus 15,000, which is a negative force, plus negative 10,000. Those are the loads that are applied to the structure. And then I need to add the force in the y direction at point A and the force in the y direction at point G. So what do all of these add up to? Well, they all have to add to 0 because the structure is in static equilibrium. But the problem is I have two variables in this equation. There's no way to sort this out yet. So I have to try and strike one of these variables. So now I'm going to go to work on the moments. And just kind of based on experience, I'm going to pick point G as my point to do my analysis on the moments. And that's largely because it's one of the support points, which will make the math easier. And because this is pinned and this is a roller, to me it's just kind of intuitive to think about moments about a pinned joint. So if we think about moments, moments are this twisting action, right? So there's going to be this counterclockwise moment, which we would conceive of as having a positive value, and this counterclockwise moment, which we would conceive of as having a negative value. And the sum of all of the moments must be 0. So let's think about what moments there are about point G. Okay, so this is, I'll make a note here, this is the sum of the moments about point G. Well, the 10,000 pound force is acting directly through point G, so effectively the length of the lever arm is 0. The 15,000 pound force is acting on a lever arm that has a length of 8 feet. So if I think about 8 times 15,000, that's 80 plus another 40, that's 120,000. Now you got to be a little bit careful about sign convention here. If I think about this 15,000, it's a negative number, right? Negative 15,000. But if I think about this 8-foot distance, you can think about the coordinate of this point H as being like negative 8. Right, it's 8 feet to the left of G. So a negative times a negative is a positive, so it's 120,000 pound-feet. And that is useful because if we think about the convention is that a counterclockwise moment gets a positive sign. So our signs are appropriate. So 120,000 plus 20,000 times 16, that's 320,000. Plus 15,000 times 24. 15,000 times 24 is 360,000. Plus 10,000 times 32 feet, that's 320,000. Plus the force in the y direction at A pushing up times this distance of 32. So if I think about A's coordinate is kind of like negative 32. And the push on A is positive, it's upward. So I'm going to say minus 32 times the force in the y direction at A. So if I look at this formula, this is a single variable, and this is solvable. So I'm going to rearrange this a little bit. I'm going to say that all of these added together sum to 1,120,000. That's a number I just punched into my calculator ahead of time. So it's going to look like this. Force in the y direction at point A is going to equal this 1,120,000 pound-feet divided by 32 feet. So you notice we're taking pound-feet and dividing by feet, and we're going to get pounds of force. It's positive 32 because if you notice I've moved the 32 over to the right side of the fraction bar, or maybe over the right side of the equal sign, or maybe a better way to think of it is I've moved the force in the y direction to the left side, which would create a sign change. Now, when I crunch this number, again, I've done this ahead of time, and I happen to know that this is 35,000 pounds. So the rollers at point A are pushing up on the structure with 35,000 pounds force. What is point G pointing up with? Well, there are a couple of ways to solve this. One way is I could rerun this moment calculation about point A, and I could calculate all of the clockwise moments generated by this series of weights, and I would know that the counterclockwise moment generated by point G has got to be equal and opposite to this series of moments. However, there's a little bit of a shortcut that I can take. If I look at the entire weight of this structure, all of these components, all of these loads add up to 72,000. Actually, negative 72,000. So, do I know what force in the y direction at A is? Yes, I do. It's positive 35,000. I'm sorry, this is negative 70,000, not 72. This is 35,000 pounds positive. So the question is negative 70,000 plus 35,000 plus this force, this force in the y direction at point G, add to 0. Well, then you can push the numbers around, or probably just by inspection you can determine that this force here needs to be 35,000 pounds. So point G is also pushing up with 35,000 pounds. Now, this truss is kind of a special case. If you look at how it's loaded, all of the spans here are 8 feet, and it's loaded right in the center with this 20,000 pound load, and then on either side at equal distances it has a 15,000 pound load, and then at either side at equal distances it has a 10,000 pound load. So because this is totally symmetric, I can make the call that this load is going to be split exactly half and half. So if you look at the reaction at A and the reaction at G, you see they're equal. They're exactly half of each is exactly half of the load of the structure. That only applies in this case because it's uniformly loaded and everything's spaced uniformly. This would not apply if you had a more complex structure. Now, the next thing that they want you to find are the forces in DE, DH, and IH. And you're going to do this by method of sections. So in method of sections, you basically draw a line that cuts the structure in half through the members that you want to find values for. So here's member DE, here's DH, and here's IH. Now what I'm going to do is I'm going to ignore everything to the right of this line. So I'm going to forget that this stuff is here. So now I'm going to look at just the system to the left of the squiggly line. And here's kind of a fundamental characteristic of structures, is that if the entire structure is in static equilibrium, then this segment of the structure to the left of the line must also be in static equilibrium. So again, I can start applying my fundamental formulas. The sum of the forces in the x direction must equal 0. We don't have any to consider at the moment. The sum of the forces in the y direction must be 0 as well. So let's start thinking about y direction forces. Well, I've got this positive 35,000 pound support. I've got this negative 10,000 pound load. I've got this negative 15,000 pound load. I've got this negative 20,000 pound load. And then I have the vertical component of this diagonal brace here, this diagonal DH. And the story with this is DH can provide an upward thrust because this is loaded axially. So if DH is in compression, it can push point D up and it can provide an upward thrust, or if it was in tension, it would pull downward. Right? So in this case, it's producing an upward and a leftward thrust. Remember, DE cannot provide any type of vertical reaction because it's pinned on its ends. If I pushed up at point D, it would simply pivot about point E. And same thing with IH. Like if I push down at point I, it's simply going to pivot about point H. So the story is there is a force in the y direction of member DH. And if I look at all of these collectively here, they all have to add to 0. So I look at all of kind of the knowns, the 35,000, the negative 10,000, the negative 15,000, the negative 20,000, and I find that this is ends up being negative 10,000 is the sum of all of these. So negative 10,000 plus the force in DH, the vertical element of the force in DH, have to add to 0, which tells me this upward thrust by DH has to be 10,000 pounds. Well, if DH is pushing point D up with 10,000 pounds force, then DH must be in compression. And if it's in compression, the push has got to be upward and leftward. And DH is kind of in a unique situation because if I look at this triangle, this DIH triangle, it's got this side here that's 8 feet. It's got this side here that's 8 feet. It's a 45, 45, 90 isosceles triangle. So one of the things that I know is that if the vertical component is 10,000 pounds, the horizontal component also has to be 10,000 pounds. So if I think about the component DH is pushing point D to the left with 10,000 pounds force, well, the other way you could think of that is it's pushing point H to the right with 10,000 pounds force. And that's going to mean that member IH has to be in tension because it's got to be reacting to that rightward push. Let's think about how much compression the member DH is in. So if I redraw this triangle for DH, I have a vertical component, 10,000 pounds. And I'll just label it as 10K for 10,000. I have a horizontal component, 10,000 pounds. By definition, these are perpendicular, and I'm trying to find the hypotenuse. So what's going to do that for me? This is good old-fashioned Pythagorean theorem. A squared plus b squared equals c squared. So if I calculate out 10,000 squared plus 10,000 squared, and then I take the square root of that sum, I'm going to get the compression in member DH. And when I push those numbers around, I get the square root of a very large sum, something like 2 million. And the square root of that is 14,000